Hi, this is the video for Lab 10 for Math 215. I want to start off with make sure that you read the import and visualize the data header before problem 1. That will be super crucial to making sure you get the data that you need to for this lab. So starting off for problem 1, we're going to create an adjacency matrix. And if you read through it, you understand that we have this set of edges structured something like this. And we want to create that into an n by n matrix. And so the way that I would do that is we first want to make our n by n matrix and preferably fill it all with zeros because that's like the default value. The way that we can do that is say we call our matrix A. We can say np.zeros. Now this will create a matrix or an array, however you specify it, filled with just zeros. And if we want to make it a matrix of size n by n, we'll want to notate it like this. The two parentheses are important so it knows that I'm not inputting two values into np.zeros. I'm just inputting a certain size, and that size is n by n. And so that's how you can do it. And what I would do is you want it for each edge list. So like say the first one is 1 and 4 for each edge. I want to increase that value by 1. So let's say I want to do a at 1, comma 4, because that's the first one that I want to increase. The way that I would increase it by 1, because we don't want to necessarily make it 1, because if it's 1, then we want it to be 2. We could do this notation, where we just take the previous value and we add 1 to it, or the shorthand in Python, if you really want to get fancy, you would do plus equals 1, which just says I'm taking my original value and I'm adding 1 to that original value. And so that's problem 1. And you'll just want to use a for loop to look through all of the things, all of the edges in your edge list. And then refer to them, if they're called like I or something, refer to them as I at 0 and I at 1. Because that's going to be your I at 0 and your I at 1. So that's problem 1. For problem 2, you'll work off of that adjacency matrix. And so yeah, say we have some adjacency matrix. This one is going to be really simple. It's like 1, 3, 4, 1. Where there's one path going from 0 to 0, three paths going from 0 to 1, so on and so forth. This is just a really, really simple one. And we want to create a vector that is the sum of all of these columns. So this one would be like 5, 4. So what I would do is say this is A. That's going to just be what our vector is called. And you'll want to call your adjacency matrix function for this part. I would create another sum vector. Yeah, I'd call it like sum vect equals np.zeros of length n. Because that's how big our matrix is going to be, is how big our vector is going to be. And then what I would do is I want to look at all the columns. And because this matrix is going to be n by n, the length of the columns is the length of the rows. So I do something for I in range of the length of A. So that will look at all the columns, or the amount of rows, depending on how you look at it. And I want to say sum vector at I equals, so yeah, let's say sum vector at 0 equals the sum of the first column. And if you remember, we can do np.sum to call that. And the way, this is always really tricky in Python. I even struggle with it sometimes. If we want to refer to, let's say, the 0th column, we want to look at everything. We want to look at all of the rows. That's what that colon means, is we're going to look at everything. So like every single row, and then comma, saying we're going to move on to the next dimension. And I want to look at every first thing in that row. So I would put 0, meaning, yeah, I'm looking at all the rows, and I'm looking at the first element in all those rows, which is the first column. So that's how we do the first one. Second one, you would do 1. But because it's a for loop, we're just going to do I, so we can look at each of them individually. Let me close that parenthesis. And so that's how you'll calculate the sum of the columns. And that will just iterate through each of them. And then you'll want to return that sum vector that you got. So that will be problem 2. problem 3 is just going to be calling this function, and yeah, make sure to use argsort and flip. That's super important, and you'll want to, the order that I like to think of, you'll want to call degree cent first, and then you'll want to do argsort off of that, and then you'll want to do flip off of that. And then you'll want to access the first element, and so I would put bracket 0 and bracket at the very end of all that. And so that will tell you the value. In this lab, it's more important than ever. Save top in degree as your formula. Don't save it as some value like 255. You want to save it as the formula that you calculated it to be, because they're going to pass in different data, and so you'll get a different number depending on what the data is. And so yeah, call them in this order, and be sure to save it as the formula, not the value itself. Next, for problem 4, they actually explained it a little more complicatedly than they needed to. They explained it as takes an input square numpy array A, takes the transpose of it, and then divides each column by the sum of the entries in that column. Now, here's what I would say. Say we have some matrix 2, 3, 4, 1. If we take the transpose, then that's going to be 2, 3, 4, 1 in that order. And so what it wants to do is take the transpose and then divide by the column of the sum of the entries in that column. So like divide by 1/5, or times by 1/5, times by 1/5. Here's what I would do. If you notice, you can either take the transpose and then divide each column, or you can divide by each row and then transpose that. So, because it's easier to take columns in Python than it is easier to take columns, sorry, I may have said that wrong. It's easier to take rows than columns. So, what I would do is I would say something, if you guys remember list comprehension, I would look at my row in A, if this is my row. So this I will look at 2 and 3, and then 4 and 1. Now what I can do is say I divided by sum of I for I and A. Now what this does is it creates a matrix where the first row, for instance, is going to look at for 0 in A, or like the first thing in A, so this row. And it's going to do that row, 2 and 3, divided by the sum of that row, which is 5. So we get the vector 2/5, 3/5. And that's going to be the first row in my matrix. And then I'll do it for the next row. We get 4/5 and 1/5. And so I would do that, and then it wants you to do the transpose. So it would swap those, and so I'd do like transpose of this whole thing. And so that's how I would go about doing this one. It's a little easier than doing the transpose and then the columns if you do the rows and then the transpose. So that's problem 4. Problem 5 is actually going to harken back a little to the lab 9, which you did previous to this. And what it first wants you to do is make an initial guess where your x sub 0 is equal to however many things you have, or n, 1 over n for each of those. And this is where I use this comprehension again. I would say you're given a matrix P. So I do 1 over the length of P, because that's how many things are going to have in it. So if it's like 5, then it's 1/5 for each value for I and P. So we're looking at the length of P, and we're saying for each one of those, I'm going to create a value that's 1 over the length of P. So if we had this matrix from before, 2, 3, 4, 1, this I says for each of these rows, I'm not actually looking for the rows, it's more of a counter sort of thing, but for these 2 rows, I'm going to create 2 entries that are 1 over 2. Or if it was 3 rows, like 5 and 6, I'd create 3 entries where they're each 1 over 3. So that's how I'd structure that. And then the rest of the problem is doing a very, very similar thing to problem 9 again, where you're just going to multiply that x times that vector p, or that matrix p, and then reset that as x. That shouldn't be too difficult. Just look at problem 9 again if you're confused. And then for problem 6, it's basically just going to be calling all of our previous functions. So they want us to first create our adjacency matrix. I would say that's like A, and I would run adjacency matrix with the n and the edge list that they give us. And then once we get that adjacency matrix, we're going to run stoich eigen with that adjacency matrix and the k that we specify. I'll call that B or something. Or sorry, my bad. We want to create the, God, I'll pronounce this. The stoich matrix. I totally bluffed on that. But then what we want to return is what we get from doing the stoich eigen with that matrix. Yeah, sorry, I messed this up a little bit. We get our adjacency matrix from running adjacency matrix function. And then when we plug that adjacency matrix into our stoich matrix function, we get our B, which is going to be our stoich matrix. And then by putting it into this function, we get the proper eigenvector after k amount of iterations. That's all you do. And then for problem 7 is going to be very similar to problem 3, where you do the whole np.flip. And just instead of calling degree sent in this instance, you are going to call page rank sent. But it will be the same exact thing. Again, use the formula, not the specific value, and be sure to put that bracket 0 and bracket at the very end to specify. I'm looking at the first value. And so yeah, that's it for problem 10. This isn't a too difficult lab, and it's actually really, really cool about all the different implementations it has into like actual useful stuff in today's world. But I hope you enjoyed the video, and I hope it helped out. See you later.